The title of this presentation is Emerging Tools for Optimizing Reservoir Operation During Floods with a case study in the Ganges River Basin. My name is Ilich. Let's go through the presentation outline quickly. This work was part of the National Hydrology Project in India, which was jointly funded by the World Bank and the Government of India with a goal to improve digital infrastructure, which implies investment in better equipment for data collection, investment in the national database, storage of data and data maintenance, as well as the use of data for various studies. We will introduce some basic concepts related to the use of reservoir optimization during floods. We'll review the required data, especially the hydrological routing and flood damage functions. We're going to focus on the accuracy of optimization models since the tests that were conducted here were based on historical data. There is going to be some discussion on the significance of the forecast lead times. We will see the results of a numerical example that used the same data but two different models. The basic concepts for reservoir management during floods are well known. The first issue is that any release from the reservoir is subject to hydrological routing. And sometimes the protected area is located further downstream of the reservoir, and it takes some time for the reservoir releases to reach this area. Along the way, there may be lots of tributaries and diversion canals which complicate this process to reach the desired threshold flows. The downstream goal is to manage the reservoir releases so as to minimize downstream damage from overbank flows. Many models are modeling this function using a quadratic form, but if you are using a linear programming solver, this function should be linearized in a way that is shown here. This is just an example. Even if you don't have the exact figures of what the damage function is, the important thing is to know these threshold flows. When we are solving reservoir operation using an optimization model, we can solve more than one time step simultaneously, as is shown in this diagram, such that the releases made in the first day, which are shown with the red color in the first channel here, will take some time to propagate to the next channel in day 2 and to the next channel in day 3. And if the affected area is located at the end of channel 3, then it's the releases in day 1 that will have to be routed and combined with additional tributaries and diversions until they reach the designated area at the end of channel 3. So it's necessary to solve the system for 3 days simultaneously. The dashed line that you see here is essentially the carryover storage, such that the ending storage at day 1 becomes the starting storage at day 2, and so forth. In this way, we are basically creating a solution with a 3 days look ahead, but we are only adopting the solution in day 1. In other words, we are proceeding with making a decision for a single day based on additional runoff forecast for the next 2 or 3 days, depending on the length of the forecast available to us. In this simple example, you can see that the solution for today should be based on some foreknowledge of flows in the next 2 days as well as in the current day. It's important to note that simulation models do not solve multiple time steps. Only optimization models can provide these kind of solutions. A little bit about channel routing. What you see here is a classical starting point for all routing methods. I'm mentioning here the so-called SAR routing method. The reference is in the bottom of this slide. The SAR stands for the Stream Synthesis and Reservoir Regulation, and this is a method that was used by the U.S. Army Corps of Engineers. It's still used in Western Canada, but it's a very effective method. From this starting equation, go through the 4 steps that are outlined here. Introduce the time of travel as a function of flow, as shown in this step 3. But you can calculate this based on the observations of average velocities, which are recorded when we measure flows, even from observations of the movement of the flood peaks during floods. This kind of relationship should be relatively easy to develop it for any river reach. Then this original equation can be converted to this form, which has the same structure as the standard Muskingum equation or Muskingum kanji, with 3 coefficients which sum up to one unnecessary condition for most routing methods. The advantage of this method is that it doesn't require any channel geometry, and we can go from low flow season to high flow season without having to recalibrate the model. We're going to review the numerical example now. We have the Son River system in India, which is a southern tributary of the Ganges basin. And there are two large dams here. One is the Bansagar Dam with 5.4 billion cubic meters, and the other one is the Rihan Dam with 8.9 billion cubic meters. And the goal in this test run was to try to maintain 9,000 cubic meters per second at the outlet of this small system. Historically, the floods were reaching more than 16,000 cubic meters per second here, and you will notice two tributaries in between which are not regulated. If it happens that the sum of flows in those two tributaries is over 9,000 cubic meters per second, we are going to have to experience some flooding downstream. But still, the idea is to minimize the total flood at the downstream section. First runs that were conducted with the two different models using the same data set identified some differences. So in order to figure out what's causing the difference, there were two sets of runs that were done. The first set of runs that we are seeing here are not using any routing routines. In other words, we are assuming steady state conditions and 1 day, 2 day, 4 day or 8 day lead times without any channel routing. And we are looking at the same solution for 1 day lead time, a slightly different solution but the same peak flow achieved in 2 day lead times, and the 4 day and 8 day lead times, as you can see, are very similar. The conclusion from this was that the 4 day lead time was sufficient for reaching the best possible solution. And also the other conclusion is that indeed there are times when the tributaries alone are contributing more than 9,000 cubic meters per second at the downstream section. We can see that from the fact that the reservoir releases during this peak are zero from both reservoirs, and we still have to incur some flood damage because there is nothing to control the flows coming down from the tributaries. Once we introduced the routing routines, and just for the sake of your reference, the length of this reach between the reservoir and the second tributary is about 120 kilometers, and then the length of the second reach is about 80 kilometers. The WebEM model was only routing these channels were shown with dashed red lines. When we conducted the run, we had to look at the data. Travel time versus flow data showed that for very high flows, travel time is much less than a day. So the daily time step was not the best here, and it was decided to use 12-hourly time step to make sure that the routing equations make sense, because you can see the flows over 5,000 cubic meters per second have travel times of 11 and 7.39 hours, which is much less than a day. So the WebEM model produced solutions which look like this. The blue line is the upstream channel, the red line is the downstream channel. For the first graph, it's the upstream set of channels, and then the same thing is seen for the downstream set of channels. You can see the effects of routing being shown as both lowering of the peak and the translation of the entire hydrograph in the downstream direction in time. And when it comes to the Kister's solution, there is an issue with using the daily time step. So the peaks are lowered, but they still show to be happening in the same time at the end and the beginning of the channel, most likely due to the use of a daily time step. The Kister's team acknowledged that this requires more calibration, and they will be working on this during the summer, possibly also with the revision of the length of the simulated time step. The final solutions at the downstream river reach are shown for 1 day lead time, 2 day lead time. You can see the comparison between the two models, the WebEM being the blue line and the Kister's RTO model having the red dashed line as its representation, and the peak flows are relatively similar. The total value of damage function, however, is both the peak and the duration of the time when the flow was above 9,000 cubic meters per second. You will realize again that we do exceed this flow of 9,000 cubic meters per second, simply because the tributaries are sending more flows than 9,000, and there is no way to handle the flow from the tributaries. However, the interesting thing is that from lead time of day 1, we're at around 12,000. Day 2, again, the peak is around 12,000 cubic meters per second, but as we increase the lead time for forecasts to 3 and 4 days, the peak has gone down to below 11,000 cubic meters per second. So the forecast lead time does help us. The longer the forecast, the better the solution. This, of course, ends with the 4-day forecast, after which the solution doesn't improve, as you can see here. These are the values of the objective function, which you can understand as the total damage from flooding. Obviously, the longer the lead time, the better off we are, and the lower the damage. And in addition to this, we are also able to see the comparison of the peak flows. Again, the general trend should be to see the lower peak flows with increased lead times, although there may be some differences here. You can see that the Kista's model has a better solution for 1-day lead time, but this is because Kista's routing works differently, and the routing has been implemented on 4 river reaches instead of 2, so we have a little more of a lowering of the peak. However, in general, the comparisons are close, and you can find more information on these two models at these two websites. This is just showing that, as a final conclusion, we do have tools that can reduce damage from flooding, and in this particular case we've gone down from over 16,000 cubic meters per second of a historical flood, which was managed by the operators, to slightly below 11,000. So this is a significant reduction, which would be based on up to 4-day forecast, and even for 2-day forecast and 1-day forecast, we are still showing 12,000 instead of more than 16,000. We should be now focusing on the improvement of the forecast models, since the optimization models for flood management are already available. I would assume that any forecasting tool could provide forecasts and put them on the website from where the optimization models could read them. And this would be the equivalent of automating the operation of dams during floods in much the same way that we see automation in transportation industries with self-driving cars and autopilots that started decades earlier and are now making the air travel the safest way to travel. This is the end of my presentation. Thank you for your attention.